Alright guys, what I'm going to do is teach you some tricks with trigonometry. In physics, the situation that's going to come up where this is most used is with force diagrams, and when everything is not necessarily pointing straight up or straight down, but at angles and such. So I'm going to show you the long way to do it, and then I'm going to show you the easy way to do it. So let's start with the long way. Okay, let's say we've got a box on an incline. We'll have like a stack of books and a whiteboard on a table, and then there's a box sitting there, but it is not moving. So we already know what direction all the forces are going. So we have one force going down always, so that's its gravity. We've got a force pushing up the ramp to keep it from sliding down, and then we have a force from the ramp that is keeping it from going through the ramp. So gravity, friction, and our normal force. But for simplicity's sake, I'm just going to say force 1, 2, and 3. So that way we can generalize this to whenever we have a force diagram that looks this way. Alright, so let's talk about the trick here. But let's talk about the long way first. So the long way is, we know this thing is in equilibrium, so all of the forces in the x equal all the forces in the y. So what we can do is we can break up the two forces on the top, F1 and F2, into its components so that we can solve for them. So we know that those two are equal because there's only two pointing in the left or the right. So these are actually small vectors pointing left and right, and then those are pointing up and down. Now, I'm going to go ahead and erase those for now. But you know that those components are vectors, so we can add them together. So this is the one way to do it. You are not wrong, but it's going to take a long time because you have to do trig on two triangles. But we're going to use a trick where we only have to use one, and we're going to do it this way. So now you can see if you turn your head to the left so that force 1 is pointing straight up and force 2 is pointing to the right, then we only have one vector that's off at an angle, and it's F3. So the reason this makes it easy is that those are the only two forces going in those directions. F1 is exactly opposite of this component here, and then that component of F3 is exactly opposite of F2. So what we could have done is, if you don't see that, then we could draw our components like this. So you can see them both ways. This is exactly in the opposite direction as the other one. So here's where the trick comes in. I don't think you remember, but that incline was at some angle, and it was at some angle theta. Well, it turns out that those two angles are equal. So this angle immediately underneath that triangle is the same as the angle on the incline. So if we know this trick, this will save us a lot of time. So again, here's our incline, and I'm going to draw the force vectors on the actual ramp here. So doing the same trick, instead of breaking up the two forces pointing up into the right and left, I'm going to just break up the bottom one so that its components are opposite of those two forces. So if our incline is at an angle, whatever angle that is, then that angle there is the same as that angle in that triangle. Okay, so we can use this to our advantage. So we can use only pieces of vectors that are useful. Instead of having two triangles, we can just use one triangle. All right. Hopefully this helps, and we will be applying this tomorrow in class.